The evolution of the physical work capacity at the fatigue threshold test, past, present, and future. There are many ways to evaluate fatigue threshold. In our study, we use EMG. EMG looks at muscle activation generated by a summation of action potentials from active muscle fibers. Our study looks at EMG amplitude, which reflects the magnitude of muscle activity through muscle recruitment, firing rate, or both. The physical work capacity at fatigue threshold is the highest exercise intensity a person can sustain indefinitely without an increase in EMG amplitude. The purpose of this mini-review is to present the past, present, and future of assessing neuromuscular fatigue for continuous muscle actions, which may have applications in both the sport and clinical settings. Specifically, we will focus on the physical work capacity at the fatigue threshold. Articles were retrieved from PubMed as well as Web of Science. Two of the co-authors have over 15 years of experience in this area, and their expertise was used to retrieve peer-reviewed articles that do not appear in other databases. The articles discussed represent critical periods in the evolution of the PWC. EMG amplitude as a measure of neuromuscular fatigue began in the 1980s by Dr. Herbert A. deVries at USC. The assumption was that the increase in EMG amplitude represented an increase in muscle activation that was necessary to maintain the power outputs. Whereas the higher the power output, the more rapid the onset of fatigue and the corresponding rate of rise in EMG amplitude. The deVries group proposed the use of a mathematical model to objectively examine the fatigue threshold, which they named the PWC. To improve the methodology, deVries et al. Used continuous exercise, thus subjects had no rest period between the workloads, meaning subjects would exercise to voluntary exhaustion. This graph shows how to find the PWC using collected data. The x-axis represents time and the y-axis is EMG. Each stage is performed every 30 watts and takes place over a 2-minute time period. The EMG is recorded every 20 seconds from the muscle, and the PWC is found using the lowest significant work capacity, as seen at 170 watts, and the highest non-significant work capacity, as seen at 140 watts. By averaging these numbers, you find the highest exercise intensity that an individual can sustain indefinitely without an increase in EMG amplitude. What followed was a series of studies that used the PWC as an index to develop endurance training programs for various populations. To further improve the work of the deVries group, Mahmutovic et al. Determined the intraclass correlation coefficient to be 0.85 and the minimal detectable change at 90% to be 34 watts and at 95% to be 40 watts. Using cycle ergometry, Briscoe et al. Was the first study to validate the PWC. Subjects cycled at 70, 100, and 130% of the PWC for up to 60 minutes on 3 occasions, separated by 48 hours. This graph shows what was found in the Briscoe et al. Study. When looking at EMG signal, again we are looking for the highest exercise intensity that can be maintained without a change in EMG. To orient you to the graph, the x-axis is the percentage of total time that each subject gets. Here, all subjects completed 100% of the time they were given. The y-axis is normalized EMG amplitude. Each line is denoted by a color, where red represents 70% of the physical work capacity at fatigue threshold, which is also denoted as EMG fatigue threshold. The green line is 100% of the physical work capacity, and the blue line is 130% of the physical work capacity. What you see is that there is not an increase in EMG amplitude with time in the green and red lines. When analysis is completed and the slope is found on the regression line, the green and red line had slopes that were not statistically significant from 0, whereas the blue line had an increase. If you go above 100%, then you are going to get an increase in EMG amplitude in the muscle as you continue to do the exercise. But if you stay at or below the threshold, you do not see an increase. This was the first study that had been hypothesized that you can maintain the exercise without a significant increase in EMG amplitude in the muscle. Kahn et al. Compared the 2-minute stage with a shorter 1-minute stage. The 1-minute stage has data collected every 10 seconds, where the 2-minute stage has data collected every 20 seconds. They found no significant difference between the protocols, meaning the 1-minute stage could be used when time is limited with a client. In a clinical setting, neuromuscular fatigue could be used to assess changes in muscle following rehabilitation. In a sports setting, PWC can potentially be used to develop training programs. Thank you for your time today.